The first topic we are going to discuss is breaking the sound barrier. These are some pictures of jets and airplanes breaking the sound barrier. Notice the cloud of condensation that forms in a cone shape behind the jet, and this is also accompanied by what is called a sonic boom, which you can hear in the next video. But what is the physics behind breaking the sound barrier? The speed of sound is the speed that sound waves travel in air, which is 761 miles per hour or 343.2 meters per second. In order to break the sound barrier, you have to go faster than this speed, which is known as Mach 1. Here's another clip of an airplane breaking the sound barrier.
Because the propagation speed of sound waves is finite, sources of sound that are moving can begin to catch up with the sound of waves they emit. As the speed of the object increases to the sonic velocity, the local velocity of sound waves, these sound waves begin to pile up in front of the object. As the speed of the object increases, waves are forced together or compressed because they cannot get out of the way of each other, eventually merging into a single shock wave at the speed of sound. When the object is passed over the observer, pressure disturbance waves, shock waves, radiate toward the ground, causing a sonic boom.
There are usually two booms, but they are typically so close together that they are indistinguishable. At supersonic speeds, there is no sound heard as an object approaches because the object is traveling faster than the sound it produces. Only after the object has passed will the observer be able to hear the sound waves emitted by the object.
The cloud you see is caused by pluripolar singularity and is caused by a sudden drop in air pressure. Under certain conditions, this drop in air pressure causes a visible sound of condensation to appear around the back of the jet. Close to and above the speed of sound, the air can't move quickly enough to flow out of the way and it must be pushed away. This builds up a wall of pressurized air, often in the cone around the plane or rocket. Behind the wall is an area of lower pressure and lower temperature. If the temperature is low enough and the humidity is high enough, water will condense to form a cloud. The reason why this cloud forms is still somewhat controversial. The cloud does not follow the airplane, rather it is spontaneously occurring because of the temperature and pressure change induced by the aircraft speed.
But how do we hear this sonic boom? How do we hear anything? The concept of hearing is very complex, and here we will look at why and how we hear what we hear on a daily basis by looking at the ear itself. The ear is made up of three sections: the outer ear, the middle ear, and the inner ear, and they all have their specific parts when it comes to hearing. The pinna and the ear canal make up the outer ear, and they funnel sound waves into the rest of the ear. These blue waves represent the sound waves. The sound waves then hit the eardrum and make it vibrate. The eardrum is like a stretched membrane, which you can visualize as like the skin cover of a drum. It separates the middle ear from the outer ear, and it is smaller and thinner than a pinky fingernail. The higher pitch of the sound, the faster the eardrum will vibrate. These vibrations are then passed on to the ossicle bones, which are the three smallest bones in your body. And from left to right, they are the malleus, the incus, and the stapes. They pass the sound on to the inner ear by vibrating as well. The vibrations then get passed onto the cochlea, which is the shell-like thing you see on the screen, and they get passed through the small window. Here's an animation of how it happens. Sound waves pass through the fluid of the cochlea and create waves, which move the hairs of the cochlea. When the hairs move, they then pass an electrical signal up the auditory nerve, which is this green line in the upper right corner of the video. When the electrical signals get passed up the auditory nerve, they then go into the brain. Then the brain determines what you are hearing and it processes the information for future use. Next, we will examine the concept of ultrasonic sound.
Ultrasonic sound is anything over 20,000 hertz. Humans cannot hear this high-pitched sound, but some animals can. One of these animals is bats. Contrary to popular belief, bats are not blind. They can see, but because they are nocturnal, it is sometimes difficult for them to see. They primarily navigate using ultrasonic senses called echolocation. The sound is so high-pitched that humans cannot detect it because the sound is not efficiently transferred from the middle ear to the cochlea. Their squeaks emit sound waves which bounce off objects and come back to them. This echo allows them to know where objects are.
They emit their sound waves, and then they hear the echo that their sound waves produce. This echo lets them know exactly where an object is, how big it is, and everything about the object, which is exemplified in this experiment that was done. A sound reflection, such as the one that is shown here by the bat, reflecting off a pool of water, would let the bat know exactly what the object is, that it's water. The amount of echo returned and how it was returned tell the bat details about the object, and other animals such as dolphins can do this as well, like what is seen right here. They can tell the type of fish, how far away they are from the fish, and everything about the fish only using their use of sound and echolocation. Ultrasounds are present in our everyday life too, but how do they work?
They actually use ultrasonic sound waves to create the image that you see, much in the same way bats use ultrasound. First, the ultrasound machine transmits high-frequency sound pulses into your body using a probe called the transducer. These frequencies range from 1 to 5 megahertz and cannot be heard by the human ear. 2. The sound waves travel into your body and hit a boundary between tissues. 3. Sound waves get reflected and echoed back into the transducer. 4. The reflected waves are picked up by the transducer and relayed to the machine. 5. The machine calculates 1. The distance from the transducer to the tissue or organ using the speed of sound in tissue, 1,540 meters per second, and 2. The time of each echo is returned, usually on the order of millionths of a second. 6. The machine displays the distances and intensities of the echoes on the screen, forming a two-dimensional image which shows a baby in a pregnant woman's stomach. In a typical ultrasound, millions of pulses and echoes are sent and received each second. The probe can be moved along the surface of the body and angled to obtain various views.
Now we will look at what is called the Doppler effect, and typically arises with things like sirens and car horns. So when a siren is far away and coming towards you, it is extremely high-pitched, but when it passes and goes away, the pitch decreases. Why? Because of the Doppler effect. Here we will look at some examples. Example 1. Notice the drastic change in pitch? Here's another example with a car horn. So here's why this happens. When an object is not moving and emits a sound, the sound waves ripple away from it in the form of concentric circles. However, when an object is moving, this is not the case. The sound waves in front of the object would compress together like you see here, because each successive wave is closer to the previous wave due to the object's motion. This would make the frequency of the sound wave a lot higher, and a higher frequency would give it a higher pitch, which is why the sound of a siren has a higher pitch when it's coming towards you. Then, when it goes away from you, each successive sound wave is further away from the previous one. They are more stretched out, which means the frequency decreases. Because it decreases, the pitch of the siren decreases as well.